Let's solve an extensive stoichiometry free response question. The complete combustion of C3H6Cl2 yields hydrogen chloride, water, and carbon dioxide gases. The question is, if 11.3 grams of this chlorinated hydrocarbon are burned in this way, in 16 grams of oxygen, how much of each product is formed? This now we see is a limiting reactant problem. So here's the question on top, and we first have to balance the equation. So you can turn off the video and balance the equation and check your answer when you come back. Here we see that 4 moles of oxygen react with 1 mole of the chlorinated hydrocarbon to form 3 moles of carbon dioxide gas, 2 moles of steam, and 2 moles of hydrogen chloride. First, of course, we have to go into the mole hole. And to do that, we first divide the 11.3 grams of the chlorinated hydrocarbon by its molar mass. 3 carbons, 36, 6 hydrogens are 6, and 2 chlorines are 71, 113 grams. When we do that, we find it's exactly 0.100 moles. Now we do the oxygen. 16 grams, if you've got 32 grams in a mole, is 0.500 moles. Next, we put these numbers into the mole hole, and of course we're going to have there a RICA table. So there's your question, there's your balanced equation, and you can see we have duplicated the balanced equation with the coefficients in the R line. We start off with 0.1 moles of the hydrocarbon chlorinated, 0.5 of the oxygen, and no product has been formed. How much oxygen do we actually need? Well, the equation tells us that we need 4 moles of oxygen for each mole of the chlorinated hydrocarbon. So we have more oxygen than we need. That means oxygen must be the excess reactant, and the chlorinated hydrocarbon is limiting. And so we're going to use all of the chlorinated hydrocarbon in the combustion, and we're going to be left with 1/10 of a mole of oxygen gas. How much product is formed? Well, we look at the balanced chemical equation, and we multiply by the coefficient ratio. In the case of the carbon dioxide, it's 3 to 1. In the case of the water, it's 2 to 1, and the same with the hydrogen chloride. Note, we are using always the limiting reactant for our calculations. Since it's limiting, the fact that the oxygen is in excess, we don't really consider that in our calculations. And when we multiply the chlorinated hydrocarbon moles, 0.1, by 3, we get 0.3 moles of carbon dioxide are formed, and then multiplying by 2, 0.2 moles of the steam is formed, and 0.2 moles of the hydrogen chloride gas. And so our product total, 0.3 of the carbon dioxide, 0.2 of the water, which is a gas, and 0.2 of the hydrogen chloride. We say the water is a gas because this is going to be very hot. It's going to come off at well over 100 degrees, so we're producing steam, not liquid water. How many grams of product does that represent? Well, we multiply the number of moles of the product by each molar mass for the products. Carbon dioxide is 44 grams per mole molar mass. So we multiply that by 0.3 moles and we get 13.2 grams. Next, the water. We have 0.2 moles of that at 18 grams per mole. That's 3.6 grams, 3 digits. And finally, the hydrogen chloride is 36.5 grams per mole, 35.5 plus 1 for the hydrogen. Multiply that by 0.2 and you get 7.30 grams. If the hydrogen chloride produced is collected at STP, what will the volume be? Well, we have the number of moles, and we know that at STP, 0 degrees and 1 atmosphere, 1 mole of any gas occupies 22.4 liters. So we multiply the 0.2 moles by the 22.4 liters per mole, and we get 4.48 liters of the HCl gas at STP. How many liters of oxygen STP would be needed for this reaction? Well, as you can see, we need 0.4 moles of oxygen. So we multiply that by 22.4 liters per mole. It's the same for every gas. We get 8.96 liters of oxygen are actually needed. Well, how many liters of oxygen STP are left over? We use the same calculation. 0.1 mole of oxygen is left over, 22.4 liters per mole, 2.24 liters of oxygen would be left over. Suppose only 6.90 grams of HCl are produced. What's the percent yield? Well, we look back and we see what our expected yield was, and we're going to divide the actual that we just saw by the expected and multiply by 100 to get the percent yield. That's 6.90 grams that we got divided by 7.30 that we expected multiplied by 100. Percent yield 94.5% to 3 significant digits. You see the power of the RICA table. Once you have the RICA table with numbers of moles used and decide how many moles are produced, you can come out of the mole hole by multiplying by the molar mass, and then that gives you grams of product. By multiplying by the molar mass to get grams, you get the total number of grams of product of each. If you wanted liters of gas at STP, you multiply by 22.4 liters per mole. Or you can use the magic of the ideal gas law, which we'll study soon, to get the volume of gas at any temperature and pressure. We'll save that for a later unit.